Okay, so in the last couple of lectures we did things which were somewhat more physical, particularly a discussion of time dilation in special and general relativity, and we also discussed this Schwarzschild solution, which turns out to be the gravitation description in general relativity for the gravitational field of any spherically symmetric static body. So I think in general it's known as the metric for a star, for a non-rotating star. But I mean, it doesn't have to be a star. Earth is also, from this point of view, Earth is also counts as a star. So those didn't require very much algebra. It was mostly conceptual. And now we have to go back to algebra because we really haven't finished describing general relativity. And there are two things that we haven't learned how to do. One is we haven't learned how to write any equation of physics in general relativity, and second is we haven't learned how to write the equation of general relativity itself, which is the Einstein equation. And we can't do either of those till we learn something more about geometry of Riemannian and Lorentzian manifolds. Again, the geometry we are discussing will be analogous for the Riemannian case, that means the spatial case, and the Lorentzian case where there is also a time. As I've said many times, the physics is different in these two cases. In one case, you are on a curved space and that's it. In the other case, you are in a curved space-time and then you have all these weird time effects. And that second thing is, of course, general relativity. So it's more general. It also allows for spatial manifolds, but it allows for space-time manifolds. And the Schwarzschild metric was a very good example of a space-time manifold. You see that it had a non-trivial thing in front of the time and in dr dt squared, and also a non-trivial thing in front of dr squared. So now we are going to just remind ourselves of a few formulae. So one of them is the transformation rule under change of coordinates. X mu goes to x mu of x prime. And we had defined v mu of x called contravariant vector, and this is equal to del x mu del x prime alpha v prime alpha of x prime. I may have written it in a different way before, with the prime and unprimed exchanged, but this is one way of writing it. And you have to memorize these formulae, but you have to also, you can memorize them by understanding what they mean. So in this case, what's happening is that so x always has an index up. Everything else gets fixed by that fact. That's a choice from the start. So there's going to be a del x by del x prime factor over here in front of whatever is there. One for each index, and since this is a vector, it has only one index, so only one factor. Secondly, this factor will have the mu index in the numerator to match this mu index. Okay, and therefore a different index alpha has to be in this denominator, which contracts with that index. Finally, is this x prime or is this x prime? Well, the one which has mu is the one which is the same coordinate as the left side. So there is no prime here. The one which has alpha, which contracts with that, has the prime. In fact, there's a kind of way that mathematicians like to write things. They often write this expression in the following way. In this form, they represent a vector, contravariant vector, by something called a vector field. They call this a vector field. And this is a differential operator. That's clear. It's basically a gradient operator, but with some function in front, with some components. And the point is, obviously this operator depends on the coordinate system, because if I change coordinates, this will change by chain rule. And this thing also depends on coordinate system because it's a vector. So it has components which will change from one coordinate system to another. But the contraction v mu times del by del x mu does not change when I go from one coordinate system to another. So it's sort of, you don't have to think too deeply why this is a differential operator. In differential geometry, of course, they will insist that this is what a vector field means, and this, they will say, is only the components of the vector field. It's just a different emphasis in mathematics. But for mathematicians, this equation basically says that a vector field is independent of my choice of coordinates. It has different components in different coordinates, but the whole operator is the same. So if you memorize this equation, you have also memorized this equation by just doing some cheating and putting this up here.
Or we can operate it on x nu.
Yeah, you can operate, exactly. You can operate it, thank you. You can operate it on x nu and you will get this equation. Exactly right. Good point. So these are the same. Okay. So that's for contravariant. For covariant, we have the relation that v mu of x is del x prime alpha del x mu v prime of alpha of x prime. And again the rule is the guy which has the same index as here, that index has to be down. So the x and x has to match with this x. Okay. Again, there's a mathematical way of writing this, which is to say, so this is the covariant vector. Mathematicians get very upset and sad if you use these words contravariant and covariant. They don't like that at all. So, but they would love this. If you have a fight with a mathematician, you show them this, and then you can be friends after that. Similarly, for this, they write it this way: v mu of x dx mu is equal to v prime alpha of x prime dx prime alpha. Again, the statement is that this is a thing. They call this a one form, and the thing is the same in all coordinates. But the thing doesn't have a formal d by dx in front, it just has a formal dx. Now, you're not really supposed to think of this as a small thing because dx is an infinitesimal. You're just supposed to think of this as a kind of representation of the information contained in v mu, the covariant vector, which is represented in a coordinate independent way. Again, if you memorize this equation, you have also got this equation. Okay, so this is just to remind you what are the transformation rules. And another thing which is very important is that in any fixed coordinate system, I can take a v which has an upper index, contravariant, multiply by the metric, sum over these common indices, and I get the version of that same contravariant vector but expressed as a covariant vector. And since g is invertible, I can go the other way also. So v mu of x is g upper mu nu of x, v nu of x. Well, g upper mu nu, I don't remember if I've introduced this. No, I think I must have introduced this notation because it's used in the Christoffel symbol. Satisfies g mu nu, g nu lambda is equal to delta mu lambda. And this relation is manifestly coordinate independent because this will transform as a tensor, this will transform as the opposite kind of tensor, and all the factors will cancel. So this is actually an invariant tensor. Okay. So all this stuff is familiar, I'm just repeating it. But now let's come to physics. And the thing is that in physics, we need to write differential equations. Essentially all laws of classical physics are partial differential equations. PDE, partial differential equation. And if we want to write a differential equation, then we have to learn how to differentiate a vector. And you might think there's no big deal about that. For example, given a vector v mu, let's start with this one. I can just differentiate it like this, where this symbol is short for that. There's also another notation we introduced once, where we put a comma. Comma nu means just act with del. It's the comma notation has one subtlety. If I put del lambda here, then I have to put lambda here. So the ordering is different. Of course, two derivatives do commute, but soon we'll encounter some kind of derivatives which don't commute. So here you're doing this first and then that. Here you're doing this first and then that. So it's slightly different, but you can easily remember the relation. So just this notation is enough. Okay. So an obvious question, under x mu goes to x mu of x prime, what happens to this object? Now when you stare at it, first of all, let's remember that if we were doing special relativity, then instead of these complicated factors del x prime by del x, we would simply have a constant matrix called lambda, which satisfies some relation, right? You remember that in special relativity, there was just a constant matrix lambda which implements the rotations and Lorentz transformations. That is what is replaced in general relativity by this, but this is not constant. This will vary because x prime depends on x, so this will vary everywhere on the manifold. Okay? This changes a lot of things. In special relativity, there was nothing to worry about because if V transforms by a constant matrix, then del nu of V will transform the same way. And del nu itself will also transform by a constant matrix by chain rule, so everything will be obvious. What it looks like, what you see is what you get. But in general relativity, it's not. And the reason is as follows. We simply have to do the calculation. So we write del nu of V mu of x. Now first we use the chain rule for this. So this is del x prime alpha del x nu del by del x prime alpha. That's just this much by chain rule. Del by del x is del x prime by del x prime, and V will change by whatever equation we had earlier, which I've rubbed out. So it will be del x prime mu by del x beta V, del x prime, sorry, del x mu by del x prime beta V prime beta of x prime. That. Okay. So that answers my question, how does del V transform? And now I just have to work out the details. This differential operator will act on this factor and will also act on that factor. When it acts on that factor, I'll get that. Okay, that's when this operator acts on this. But as you know, a derivative distributes over the product of two functions. So there's also a term where it acts on this, and that term is this. Okay, I've used a little trick which I often use to help myself not make mistakes. They are Greek letters, mu, nu, lambda, rho, sigma. These are from later part of the Greek alphabet, and alpha, beta, gamma, delta. These are from earlier part. So I try to make sure that my indices are. This is up to you because these are all contracted. So you would be free to call beta as anything you like, some other thing, as long as it's the same thing here and here. But this is just a trick so that when you check your equations, you'll have the alpha, beta, gammas on the primed coordinates and the mu, nu, rhos on the unprimed coordinates. Anytime you write an equation, it's always a good idea to check that the indices on the left side match the indices on the right side. And that happens after you forget the ones which are contracted. So nu and mu are uncontracted, they match the left side. And alpha is contracted, beta is contracted. So both disappear because they are contracted means this, they are summed over. So they are not free indices anymore in the equation. Okay, so you have to check very carefully every time that both sides of any equation have this index placement. But that isn't enough for life to be good, because now you see a problem. Supposing the vector was constant. After all, constant vector is the easiest kind of vector you can think of. Then constant independent of all the x's, t, x, y, z. Then del nu of v would be 0. In the new coordinates, this term would be 0, but this term would not be 0. Okay? Because this term has a piece that is there even if the vector is constant. Or actually, it's better to look at it the other way. Supposing, anyway, the point I'm making is that this transformation doesn't guarantee that del of v equals 0 implies del prime of v prime equals 0. So, constancy of a vector is not preserved under, so I'm going to introduce this abbreviation. This is general coordinate transformations. Any invertible change of coordinates. Constancy is not preserved. Okay. That's a little bit worrying, and it's not something which happened in special relativity. It's also not something which happened when we were studying rotationally invariant systems. Both in rotationally invariant and Lorentz invariant systems, if a vector was constant in one frame or one set of coordinates, then in a rotated frame or a Lorentz transformed frame, it was still constant, because the matrix multiplying the vector to go from one frame to the other is a constant matrix. So constant goes to constant. Here it's not so. So that's a bit strange, because imagine that I have a physical situation and these are my x coordinates and these are my x prime coordinates, and in this situation I have a bunch of nicely parallel vectors. Okay, they are meant to be nicely parallel, don't trust my drawing. This. Now I go this way, and here let's say they start looking like that. That's not pleasant, and it makes it very hard to do physics, because as soon as somebody says let's take a constant field in the laboratory, you'll say, oh, you mean constant in this or constant in that? So this starts to introduce a lot of complication to our discussion. Okay, and it also means that if any equation of physics contains this factor, that equation can't be true in all frames. Because supposing, in fact, take a very simple case. The simplest case you can think of is that there is some vector, and an equation of physics says that del mu v mu equals 0. You are supposed to find these solutions to this equation. Suppose. Or you could have a simpler equation which is v nu del nu v mu equals 0. This is a vector equation. Something like that. It could be an equation of physics. We are not going right now into detail what are correct equations. But the problem is that this does not go to v prime alpha del alpha v prime beta equals 0 because of this inhomogeneous term. Now this can't therefore be an equation of physics by a principle which I told you in the very first lecture, which is universality of physical laws. The whole notion of both special and general relativity are to generalize physical laws to be universal in all frames. In the case of special relativity, all frames means all inertial frames, but for general relativity, it literally means all frames of reference. Okay, and we can't have a law therefore that looks like this. And now one thing to realize is that all physical laws look like some function equals 0. Any law you have ever thought of, take the right side to the left side and you'll get something equals 0. Let's look at Newton's equation. Fi minus mx double dot I. In a non-relativistic physics, this is 0. Why is this a good law? Because it's rotationally invariant. What is the good thing? That under rotation, this goes to both f and x transform the same way by the rotation matrix omega ij. Now, if this was 0 before, then this whole thing is still 0 because that's an invertible matrix, so therefore this thing has to be 0. So the physical law is the same in all rotated frames, and that's a great thing about Newton's law. It's true of any law which involves vector science. If you ever wondered why all your laws like Maxwell's equation and laws of classical mechanics involve vectors, it's for this reason that under rotations, it's not that the vector remains the same, but the law remains the same. The fact that this is 0 remains the same. F changes. Because F is in earlier coordinates, it's the force in some direction. After rotation, it's the force in some other direction. But luckily, this also rotates. So everything rotates the same way, so that the relation between force and acceleration hasn't changed. This is really important. Okay. And this problem, that ordinary derivative of a vector is not invariant in the general coordinate case, means that we can't have laws of physics which will satisfy the principle of equivalence, for example, or just which will be coordinate invariant if they are based on such quantities. Now let's ask the question why. What is it about geometry which makes this issue so difficult? Now it's very hard to draw pictures of space-time geometry, but this is a problem already in spatial geometry. You could just replace mu and nu with I and j, and everything I've said is still true because this calculation is exactly the same. You can do this for a normal spatial Riemannian manifold. In fact, that's where Einstein got it from. Riemann had done it. Okay? So why? So let's look at pretty much the only manifold we are ever able to draw properly and think about, which is the sphere. So I'm sure you know this riddle, which is that I have a house such that all four windows on all four sides look towards the south. Where is my house, or what color are the bears? So anyway, the house is on the North Pole because all directions point south. So I can pick one vector arbitrarily which will point south automatically. Now that vector gives me a direction. The whole point of a vector is to give me a direction. So I can follow that direction and keep taking the vector until it actually does reach south. I don't have to go that far, but I can follow the direction with this vector. Now think a little bit, what is the actual direction of this vector as you see it from outside the sphere? Well, here it was actually pointing that way, tangent to the sphere. Here it's pointing that way. Here it's pointing that way. And here it's pointing that way. It's going on bending. But it's actually the straightest vector you can get from north to south, yet it's going on bending. This phenomenon of bending is exactly the phenomenon induced by curvature, or the fact that this has a non-trivial metric, and it is the reason why this kind of problem arises. Because if I said this is constant, I don't even know what it means because I can't compare a vector here and a vector here. They actually live in different spaces. The tangent space here is a plane touching the sphere. Here it's a plane like that touching the sphere. I have to have some rule to identify this plane with that plane. Okay? You may say in the case of a sphere, it's very easy to guess the rule because sphere is so symmetric, but you need it in general. Maybe a very weird manifold. You need a rule to identify the tangent space at each point. You may or may not appreciate this reasoning. It's just a reasoning to explain why constancy of a vector is not preserved under GCT. Yes?
Can I think of it like a general coordinate transformation not only takes me to other inertial frames but also accelerating frames, and hence the laws
Yes.
of physics are
Yes, you can think of it that way. A general coordinate transformation, good, that's a very good point. A general coordinate transformation takes me from very good, from a inertial to non-inertial frame or other way around.
there's no risk.
So in fact, very good. Actually, here's a very simple example which I was going to come to later, but since you asked this question, let's do it now. So supposing I have a velocity vector u mu equals dx mu by d tau. We have discussed this by drawing x mu is some path on a manifold. and I have a velocity vector and I ask what is the acceleration, I would think that the acceleration should be d u mu by d tau, which is d2 x mu by d tau squared from this relation. Yes? So therefore, if the acceleration is 0, then this quantity should be 0. Okay, but we have seen an equation which contains this quantity, which is a geodesic equation, but that equation doesn't only have this term, it has one more term involving a Christoffel symbol. That's exactly the purpose of the Christoffel symbol, to make this acceleration the same as a vector, to make it into a vector in all frames. What you said is that the naive acceleration defined like this can be 0 in one frame and non-zero in another frame. But then it can't be a vector, because we have seen that vectors transform by a factor in front. So if a vector is 0 in one frame, it's 0 in all frames. But we know physically that acceleration, if 0 in one frame, is not 0 in all frames. So there can't be any equation which sets this to 0, and which is claimed as a law of physics. And in fact, on the contrary, there is a geodesic equation which actually is d2x mu by d tau squared plus gamma mu nu lambda dx nu d tau dx lambda d tau. And this equation being 0, we have already proved is invariant under all change of coordinates, precisely because this is not invariant and this is not invariant, and the non-invariance or inhomogeneous terms actually cancel when we add this. So in fact, this is an example of what I have been saying, and in fact this is a special case of what I am going to do today. We'll come back to this equation in a little while. Any more questions? Yes. Yeah. Exactly. If something is 0 in one frame and not in another frame, you can choose a frame where it's 0 and work in that frame. But for example, for a vector, as per the rules I gave for transformation of a vector, if the vector is not 0 in one frame, it can never be 0 in another frame. At best, it can be 0 at a point. But if it's identically 0 in one frame, then it cannot be identically 0 in, then it cannot be if it's identically 0 in one frame, then it's identically 0 in all frames. That's what a vector is supposed to do. So laws of physics must deal with those quantities. Now when you interpret the laws of physics, it's completely different. You can ask what is an observer experiencing in some situation. Now the observer has some coordinates tied to them, and they may experience something different depending on their coordinates or someone else's coordinates. But those results should be extractable from the laws of physics. They cannot themselves be the laws of physics. Otherwise, I'll have to write my laws of physics for this observer, that observer, moving observer, stationary observer, all imaginable observers. That's what we don't want. And that's what we don't want. Okay, so what's the solution? Well, the solution is extremely simple. We define a new kind of derivative, d, called the covariant derivative. And its definition is, first of all, it's the ordinary derivative, and then there is one more term like that, where gamma is our old friend, the Christoffel symbol that we've already defined.
So we're basically fitting this.
Yeah, it's very much like that. I'll tell you the exact map between this and that in a few minutes. Here, this is just the gradient. That you will find that it's the directional gradient. If I dot the whole equation with v again, then I'll get that. But right now, it's the covariant derivative which allows me to take a vector and transport it to any neighboring point on the manifold in any direction, where nu is the set of all directions. So it's the gradient. Gradient, as you know, takes any function or vector or anything and gives me different variations of it in all possible directions. It's a directional derivative. So that's what this is. How to remember? This is again something you have to remember. But you will see quite easily that if you just write gamma v, it won't be difficult to remember how to put the indices in. because we had an index up, so it must be up. Then second thing is that the Christoffel symbol actually acts on this index. So this index must be a different one. You can choose any name for it. And that same index must be one of the two lower indices of the Christoffel symbol. Now you have to fill in mu and nu, but mu is up, so it has to be here, and nu is down, so it has to be here. It's easy to remember this equation that way. And you do need to remember it. Okay? And there's a plus sign. So this is the covariant derivative. And the claim, which I've justified a little more in the notes, this implements parallel transport on the manifold. Which means if this quantity is 0, then the vector is in a certain sense same at one point and another point. Even though it's living in different tangent spaces, it just gets identified with itself. Called parallel transport. There are many descriptions, yes.
So in the sphere case, you embedded it in.
Yeah, in the sphere case, actually, that's a slightly misleading case because I embedded it in R3 so that I can see the effect. But the more general statement is that the tangent space is the abstract space created by just taking an infinitesimal change of a function at a point. Okay? So then in that definition, it's again different at every point. And you have no canonical way of defining sameness of vectors or parallelness. And let me give you an example with the sphere, but a better example. You know that there are many different maps of the Earth. So let's assume this is Mercator projection and this is somebody else's projection. Can anyone remember any other projection? I was taught this in school, so it's stuck in my memory. You know that there are different projections for maps of the Earth. Okay. Now, simple fact, and you know that these projections distort the size, they either distort the size or the shape. You can't have everything look the same because everything is really on a sphere. Okay. But for example, Africa might be larger than it seems, smaller than it seems, or whatever. And people, I don't know if you follow all these interesting pages, but say on Facebook, there's a wonderful page called Terrible Maps, which relates, which tells you odd things about maps. So they may try to take India and fit it on Africa, but with the correct size, and you'll get a shock. Or you see that something, Greenland or Canada, something much bigger than it seems, or something like that. Now, what you can do is take this and draw a set of arrows, all of the same length and all parallel. Now it's clear what you're doing. You're drawing parallel arrows on a plane. There's no ambiguity on a plane. Now find these arrows in the new projection. What is the new projection? It's basically obtained by taking the original Earth, going back from this to the globe, to the surface of the Earth, and then going from that to this new map. Okay, where the shapes are distorted relative to that one. And you will find that your arrows now in fact have done exactly what we didn't want. So if you tell somebody, I want all my vectors to be parallel on a segment of a map, they will not agree depending on what map they are using. This is exactly the same phenomenon. Okay, and I'm sure you have seen these very nice explanations that if a plane has to go from Beijing to New York, you think it will go straight on the map, but will actually go this way, not because the airline is trying to lose money, but because actually with the metric, that is a shorter distance than this one. That is actually the geodesic and not this. So just hundreds of ways of seeing the same thing. Soon as you start to venture into differential geometry, Riemannian geometry, you will realize the same thing in many ways. But my claim is that this guy transforms as a vector. So we claim this is actually equal to del x In other words, it transforms as a second rank tensor with one covariant and one contravariant index. You can easily see by inspection which of these is the one acting on the covariant index and which is on the contravariant index. But there has to be one factor of each. And you know that the x prime versus x gets switched if I go between covariant and contravariant vectors. So this is the transformation. Now, it's a tedious thing to prove, but not difficult in any way. And it's proved in the, well, at least I've written how to prove the steps in the notes. I'm not going to go through them here except to say the following. This has one term that makes it transform like a tensor and one inhomogeneous term. This guy has also one term that makes it transform like a tensor and one inhomogeneous term. We have already worked this out several lectures ago when we studied geodesics. Those two extra inhomogeneous terms just cancel between them. Therefore, this is true. Therefore, an equation of physics which says d nu of v mu equals 0, if true in one frame, is true in all frames. You can see it from this. If this is 0, you shouldn't worry that this might be 0 because these are all invertible matrices because the change of coordinates allowed has to be invertible. So these can't be 0, nor can they have 0 eigenvalues. In fact, this equation can be perfectly inverted by just taking these on the other side. Okay, so if this is 0, obviously that is 0, and by taking this the other side, I see that if this is 0, then also that is 0. So both ways it is. So laws of physics can and in fact must be written in this form. And just for those of you who know Maxwell, how many of you have encountered Maxwell's equations in relativistic form? Yeah, so many of you have seen it. And you probably know that the equation looks like del mu f mu nu equals 0. Okay, where this is del mu a squared. Okay, well, all we have to do to make it relativistic is to replace, or to make it general relativistic, is to replace all of these with these. Now we haven't yet decided how D acts, so we haven't actually, maybe this is not the best way. I think better is to write it like this. I'm getting a little ahead of myself because we haven't yet decided how the covariant derivative acts on a covariant vector. We've only defined it on a contravariant vector. But we'll see in a moment that this actually is the same as the covariant derivative. So whenever something is antisymmetric, the covariant derivative isn't needed. Okay, and this will become D. And that's it. So if we want to write Maxwell's equations in presence of space-time curvature, it's as simple as that, nothing more to it. And now the Maxwell's laws will be full of affine connections all over the place. Every law of Maxwell will have some affine connections here and there, but they're all calculable. If I give you the geometry of, if I give you the metric, they're all calculable. And this is actually how light interacts with gravity. It's amazing what a major result we have got from such a minor assumption. Minor in the sense, very simple assumption that we have to replace everything by covariant derivatives. It simply teaches us that one of the most famous equations of physics, now we know it in presence of gravity. We knew it only in absence of gravity. Now we know it in presence of gravity. And well, you should have fun decoding this quantity. It has many terms. Okay, but eventually that's the equation. This is just a side comment. The reason I was getting ahead of myself is that I haven't yet told you what is D on anything except a contravariant vector. So let's try to find something like D lambda. So let's try to first find it on a tensor. What if we have a tensor which has like two upper indices? Okay. So for that, we'll start with a very specific tensor. We'll take two vectors and multiply them to form a tensor. Not all tensors are like this, but there's certainly one kind of tensor, simple kind. Okay. And we'll assume that D satisfies a distributive property. Okay, we actually don't even, we won't assume that, we'll actually prove it. So, first of all, So I'm going to write, okay, sorry, we will assume that it follows a distributive property. So I'm going to assume that this is d lambda v mu, w nu. Yeah, we haven't defined it, so we have to assume something about how it's defined. I want it to behave like this. This is how an ordinary derivative would have behaved. Derivative on a product is derivative on first guy or second guy. Okay. So I'm going to assume that this is distributive. And now I know what's on the right hand side. I can expand it. So del lambda v mu, w mu, plus gamma lambda mu alpha, rho v rho w mu. Then the next term I have to expand out. So v mu del lambda w mu plus gamma mu lambda rho v mu w rho. So I wrote this d here, and in the next line I wrote this d on w. Now the ordinary derivative is certainly distributive. So this term plus this term is nothing but del lambda of v mu w nu. I can just collect them. And I have two more terms. One is gamma mu lambda rho v rho w nu, and one is gamma mu lambda rho v mu w rho. No, something is wrong. Gamma nu. Yes. Good. So we've actually found the covariant derivative of some second rank tensor, and we notice that it's in a form which is easily generalized to any second rank tensor. And it can't be that the rule is different for different second rank tensors. All tensors of a given kind are supposed to have the same properties under transformation. So also the covariant derivative must be the same. So this tells me that d lambda of any tensor t mu nu is del lambda of the same tensor plus gamma mu lambda rho t rho nu plus gamma nu lambda rho t mu rho. And what is this? First of all, covariant derivative always has a term which is the ordinary derivative. Because we might be in flat space where there are no gammas, where the metric is just eta mu nu, and then everything has to be normal again. Can't be something completely weird. So this term must be there. And then there's one term for every index on this guy. You pick mu, replace it by something, put that thing here, fill in the other indices, leave the other index the same. Here you pick the second index and do the same property. Think of gamma as something which acts one by one on every index, and there's a term with a plus sign for every such index. This you can easily generalize to 10 or 100 indices. Yes?
When that
Which one?
last term.
Yes, this one?
The next time.
This one? Absolutely. Thank you. This happens all the time. But yes, thank you. Good. Shows everyone is following well. So this is the rule for a second rank contravariant tensor. And as I said, you can easily memorize this rule, and then any tensor with all indices up, you know its covariant derivative. The reason I bring in tensors is that, well, there's one tensor which is very important in physics, that's the metric tensor. Without that, you can't do general relativity. But there are many other tensors. There's what is called the stress energy or energy momentum tensor in physics. I don't know if you have done any course in fluid mechanics, but it plays a role there. It plays a role in many things in physics. And it's a second rank tensor like this, and so this will be the rule. But this is all for people with upper indices only. What should we do for people with lower indices? That's the last step, and then we can conclude our discussion of covariant derivatives for today. So let me leave this one up. The product rule, I think it was easy to follow, and you can easily generalize it yourself. Now let's consider these two vectors v and any two vectors v and w, and then let's take their scalar product v mu w mu, inner product, summing over mu. So what kind of object is this? It's no longer a vector or a tensor, this is a scalar. On a scalar, there's only one kind of derivative, the ordinary derivative. There's nothing like covariant derivative, even in a curved space. Why is that? Let's think. Can you think why for a scalar there's only one way to differentiate it? Yes, good. One answer is that if it's constant in one coordinate system, because it doesn't change. Phi prime of x prime is phi of x. That's the rule for a scalar. So if it's constant in one, it's constant in all. That's already a good thing. Secondly, just thinking intuitively, I can very well compare the temperature in Pune and the temperature in, I don't know, Paris. Okay? There's no need to worry about what coordinates I'm working in, because temperature is not a coordinate, it's a unit dependent thing, but not a coordinate dependent thing. It doesn't change if I rotate my system. Okay? So scalars are like that. So there's only one derivative, one way to differentiate it. But what I'm going to do is I'm going to also call this as the covariant derivative of a scalar. Namely, this is the same as that. Okay, so we learned that the covariant derivative is some kind of animal that first it finds out what it is acting on and then it decides how it acts. Okay, already we've seen that with a tensor, it has two extra terms, not one. On a vector, it has one extra term. On a scalar, it has no extra terms. Okay, so I'm going to write this and then I'm going to use the distributive property again. Now, out of all the quantities in this equation, the left side I know, because this is just ordinary derivative, there is no mystery. This thing I have defined for you up here. This is the covariant derivative on a vector with upper index. This thing I don't know. I'm trying to find it out. So I can solve for it. This is just going to be equal to that thing minus that thing, all of which are known. So it's a simple exercise. And you get an interesting result, which again you will eventually have to memorize. D nu of v mu is, of course, ordinary derivative always, minus gamma mu lambda v lambda. This time there's a minus, and the index contraction goes differently because v was a covariant vector. What I'm trying to differentiate had a lower index. The rule for the connection term is always to replace the lower index and dot it with a identical index on gamma. But now it's dotted with the upper index. The two lower indices are free and they match the left side. And in this case, the order doesn't matter because this is symmetric under exchange of mu and nu. So you can be careless with the order. And these two rules are enough to know the rules for covariantly differentiating anything. Okay, now it looks like a lot of formalism, but the more you look at it, the more you'll realize, first of all, it's natural. Secondly, it's needed because I just told you, you can't write Maxwell's equations in presence of gravity without that. If you couldn't do that, how are you going to ever make a theory of how light behaves in the presence of gravity? It's a very ancient question. Is light attracted by gravity? And it's a very puzzling question because once we know that light is made of massless photons, we would think that it's not attracted by gravity because mass is what makes things attracted by gravity. But it's not so. Light is attracted by gravity and it in fact bends in gravity. Okay? And bending of light was one of the most famous tests, earliest and most famous tests of general relativity. I think, if I'm not mistaken, that's the one that involved an expedition where they ended up in a war zone and got kidnapped. Have you read about this thing? Huh? In Russia? Yeah. And then apparently, I don't know, the way I read it, the people who caught them, the soldiers, were like, oh, you're going to do a test of general relativity? Sure, you can go. You're not involved in this. So you see, times were different then and now. So, read about it. I might have made up slightly. Okay. So I hope you are convinced that these two rules tell me everything. Now if I have a tensor with many lower indices, there will be one minus gamma term for every lower index. If it has mixed indices, many upper and many lower, there will be a plus gamma term for every upper and a minus gamma term for every lower. And you just have to write them all. Okay. So now the last thing, which is a very cute exercise. Okay, there are a few more things which relate to geodesics. I don't have time since we have only 5 minutes. But it's all in the notes and it's all very easy once you have got through this. So read it from the notes. But let's ask the following question. What is the covariant derivative of the metric? It must be interesting because we have a metric and what is its covariant derivative? So first of all, the rule, very simple. So again, as you can see, this is when it's acting on the index mu, we get lambda mu here and that index gets replaced and contracted. When it acts on the index nu, this index gets replaced and contracted. So that's how we write it. So this is the answer. Now, do you remember how gamma was defined?
Yes.
Okay, so let me remind you in case you have forgotten. Gamma rho, gamma, it doesn't matter, but gamma lambda mu nu is half G lambda rho, G rho, yeah, show that please. Rho mu or arg mu plus G rho mu minus G mu gamma rho. So it involves the inverse of G, but if you see, these are all first derivatives of G. This is also a first derivative of G. Okay. Now you can calculate it. It's a long calculation because here's one particular derivative term of G. Here there will be 3 from this, and here there will be 3 more with some other placement of indices, and then there will be a lot of contracting between lowered metrics and upward metrics and all that, and you will get some answer. But you can guess the answer. How do you guess the answer? Just looking at this expression, which is all made up of first derivatives of G, we've already said that there's a frame in which all first derivatives of G are 0. If that is so, then all terms on this right hand side are 0 in that frame. Therefore, this is 0 in that frame. But this is a tensor, so it's 0 in all frames. So it's identically 0. Yes.
There's a frame where the tensor is 0 at a point, right?
Yes. Yes. But exactly. But at that point it's 0. Therefore this is 0. Now I can pick another point and choose a different frame where that is 0. Therefore this is 0. And I can do it point by point. At any point you like, I can find a frame where this is 0, but being a tensor, it's therefore 0 at that point in all frames, and therefore at all points also. A very beautiful result. So we express this by saying that the metric is covariantly constant. It's pretty obvious why we use this language. And one more thing, just a matter of notation, because you might read in books, d nu v mu is often written as v mu semicolon nu. Ordinary comma means ordinary derivative, semicolon means covariant derivative. So in that language, similarly, d nu of v mu is v mu semicolon. It just makes it much shorter to write. It's very tedious to write all this stuff. Okay. So the covariant constancy of the metric is a very, very useful notion. Let me show you one quick application and you'll see why it's so helpful. Supposing I take a vector v mu and I relate it to its contravariant version by this. And now I take the covariant derivative on both sides. Okay. Now on the right side, by distributivity, this is d lambda g mu nu plus g mu nu d lambda g nu. But we've just shown that this is 0. So if I covariantly differentiate a covariant vector and I covariantly differentiate the contravariant version of it, there's no difference. That's also raised and lowered by g. The fact that g is space-time dependent doesn't spoil that relation. So I can, these two things commute. Raising and lowering commutes with covariant differentiation. Makes writing the laws much easier. Okay, we are still not done because we have to still reach second derivative. Now everything becomes super easy, and tomorrow we will introduce the Riemann tensor, and then we'll be done with all the formalism we need to understand GR. But I hope that the geometry of this was understandable. I don't expect you to grasp all the details of these manipulations, but you need to go through them on your own and work them. As I posted on the classroom, I won't be questioning you on this week's things in the quiz on Friday. Sorry?